Sample problem 4.3. Write the molecular, ionic, and net ionic equations for the reaction that occurs when aqueous solutions of lead acetate, PbC2H3O2, and calcium chloride, CaCl2, are combined. Okay, so this is the sort of ultimate type question in precipitation reactions. This is the idea of precipitation. So what happens is when compounds dissolve in water, sometimes ions can exist in the water that are so attracted to each other, they will react with each other and form a solid and precipitate out as an ionic compound. Okay? So let's take a look at how we approach this problem. We're going to need a few things. One we're going to need is knowledge of the charges of the ions. We're also going to need the solubility guidelines. So I have the solubility guidelines up here so we can refer to those when we need them. Okay. And then we have to have some experience writing equations. So what I'm going to do is I'm going to solve the problem here. Excuse me. So let's go through it. So step 1, we're going to write out the molecular equation. There's a certain procedure that you're going to use for doing these types of problems, or this type of problem, and that is the first step is you draw the molecular equation. So here's how you draw the molecular equation. You write the two substances that are given as reactants. So see how it says lead acetate and then gives you the formula, and then it says calcium chloride and gives you the formula? You write those two formulas down as reactants. Order doesn't matter. It doesn't matter which one you put first. So I'm going to do the lead acetate first. And then I'm going to do the calcium chloride second. Okay? Then you put an arrow, and then after that we're going to write out the chemical formulas for the products. Okay? Now here's the idea. This is a precipitation reaction. When you have two ionic compounds reacting with each other, it is possible for them to precipitate out. So what you do is you break up each of the reactants into two parts. The metal is the positive, the non-metal is the negative. The metal is the positive, the non-metal is the negative. Positive, negative, positive, negative. Switch partners. That's the terminology if you want to use that. The technical term is double displacement or double replacement, but the point is the positive here is going to go with the negative here, and the positive here is going to go with the negative there. Switch partners. Now, to me, it looks like there's not enough room over on the right side, but I'm going to try to squeeze it in there. So I'm going to write the PB with the Cl. Switch partners, right? And then I'm going to write the Ca with the acetate, C2H3O2. But here's the problem. If you take a look at both of these formulas, see how there's two acetates and there's two chlorides? Why two? It has to do with the charges. We have to know what the charges are. Okay? Now, some of these are easy to figure out. The charges work in the following way. If you have lithium, sodium, potassium, rubidium, and cesium, those are +1. If you have magnesium, calcium, strontium, and barium, those are +2. So we know the calcium is +2. I'm going to write the charge right up there. Okay. Now, what about other ones? Well, there's some others that are easy to figure out. There's fluoride, chloride, bromide, and iodide. Those are all -1. That's from the periodic table. That's where I'm getting this information. So this column 7A are -1. Column 1A is +1. Column 2A, I'll just write it 2A, they're +2. Okay? So chloride must be -1. Okay. Now, if you take a look at, let me put this over here, the way the logic is, positive charge in a compound has to equal negative charge. So the reason there's 2 chlorides is because each one's -1, but the calcium's +2, so you need 2 -1s. So the same would be true over here. Acetate is -1. This is a polyatomic ion, and it's -1. And there's 2 of them, okay? So if there's 2 of those, that means that the lead must be +2. Okay, so here's what happens then. If the lead is +2 and the chloride's -1, that means we need 2 chlorides. And if the acetate is -1 but calcium is +2, that means we need 2. We use parentheses for polyatomic ions, then we need a 2 there. Okay? So let's clean this up. This is a lot of mess. You can read that 3 or 4 times if you want to go over it, but I'm going to write this equation in such a way that we can fit it all in here. Okay? So again, you write the chemical formula of the first one. Then you write the chemical formula of the second one. Then you write an arrow, and then you switch partners. Figure out what the charges are. That way you know how many go together. Okay? There you go. So there's the molecular equation. Okay? Now, is it balanced? Let's see. There's 1 lead on both sides. There's 2 acetates on both sides. There's 1 calcium on both sides, and there's 2 chlorides on both sides. So it is, in fact, balanced. Okay. Next step, put states of matter. If it's soluble in water, we write AQ. If it's insoluble, we write S. Okay? S for solid. Okay, so be careful. Soluble is not S, insoluble is S, because S refers to the state of matter, which is solid, not to whether it's soluble or not. Okay, although they are connected. So how do we figure out if these things are soluble or not? We did that in the previous example, sample problem 4.2. So we have lead, we have acetate, we have calcium, and we have chloride. Those are the ions, those are the 4 ions that are in this particular problem. Okay? So we look up things for lead, we look up things for acetate, we look up things for calcium, and we look up things for chloride. So let's come back up here. Okay, so looking through here, there is, in the second rule at the top, 4.2, acetates are always soluble. So anything with acetate is soluble, no exceptions. Now, chloride is soluble unless it's with silver, mercury, or lead. Okay, so chloride, if it's with lead, it's insoluble. Okay, so we come back over here. Anything with acetate is soluble. So that one's aqueous. Chlorides are soluble. Chlorides are soluble unless they're with silver, mercury, or lead. Well, that's lead, so that's insoluble. And then acetates are always soluble. Okay, so even with all of that, there's not enough room for me to write this down really properly there. It takes up a lot of space. Okay, so now that's the molecular. We just did the molecular. That's called the molecular equation. All right. What's next is to do the ionic equation. And the ionic equation, that's done from the molecular. You do the molecular first, and then you do the ionic. And here's all we're going to do. Separate all soluble compounds into ions, into separate ions. Separate. Okay, you're going to separate them into separate ions. Only the ones that are soluble. So those are the ones that are aqueous. Remember, soluble, the way we indicate in a chemical equation that something is soluble is we write AQ. Okay? So, which ones are soluble? 3 out of the 4 are soluble, so you separate them into ions. So lead, acetate. Now notice The 2 comes out in the front. Okay, so the subscript for a polyatomic ion comes out to the front of the polyatomic ion when you do the ionic equation. Calcium. And then there's 2 chlorides. So again, 2 chlorides. See how much room that took up? That took up an enormous amount of room. So I'm going to have to put the arrow here and then do the products. Okay, reactants and then products. So the next one is lead chloride, PbCl2. That's solid. That one is not going to get separated. The solid ones don't get separated. And the reason is solid means it doesn't dissolve, so it's not aqueous. So PbCl2. You just bring it down just as it is there. Next one is the calcium acetate. That is soluble, so calcium 2, aqueous. Again, there's this 2 here, so 2 acetate. Okay? That's called the ionic equation. The ionic equation shows all of the ions that are dissolved into the water, and then it also shows the solid not dissolved in water. Okay? It's going to be very, very long. The third part is called the net ionic equation. So let me move over here. You get the net ionic equation from the ionic equation. So this is very sequential. You do molecular first, then you do ionic, then you do net ionic. And here's what you do. Cancel ions on both sides. Any ion that's on both sides, cancel it. So take a look at the ionic equation. See how there's a lead 2 on the left side but not the right side? So you can't cancel it. But there's 2 acetates on the left side and 2 acetates on the right side. So you can cancel those. There's a calcium on the left, there's a calcium on the right. You can cancel those. There's 2 chlorides on the left, but there are no 2 chlorides on the right. The chlorides are in a different chemical form, as is the lead. So it looks like we can cancel the acetate and the calcium. So you just write down what you don't cancel. The ones that don't get canceled are the ones that you write here. So the lead doesn't get canceled. The chloride doesn't get canceled. And then the product is PbCl2. So you're canceling everything that's identical on both sides. It has to have exactly the same chemical formula, exactly the same state of matter, and exactly the same number. Then you can cancel them. If there's any difference, for example, PbCl2 is not the same as Pb2+, then you can't cancel it, and that's called the net ionic equation. The net ionic equation is simpler than the ionic equation, and that's the third part. So there's 3 equations that you're practicing. You're practicing the molecular, you're practicing the ionic, and then you're practicing the net ionic equation. Those are the 3. And again, you got to do it sequentially.